Let's look at the R code for KNN classification. Of course, we are going to use this simple file, vacation trip classification.csv, and we read the data, and the data looks like this. Again, there are two predictor attributes, both are numeric. So initially we just take a simple case, and the result is buyer or non-buyer. Okay, so first step we do is we scale the attributes. Okay, so actually when we use the function scale, it actually normalizes in terms of terminology. So scale, what it's doing is creating a normalized or standardized attribute. Okay, and it's common practice to use the word z to refer to a normalized value. So I called the normalized value as income underscore z, family size underscore z, right? So these are going to be our predictor attributes. That's the target attribute. Okay, so we're going to do the partitioning, library caret seed to 2015. And you already know that in order to create a partition, we supply the value of the target attribute. And we're doing 0.6 for the training A partition. And then we'll do 0.2 for the training B and test. So we're doing this. And in order to create the, to take the remaining of this and then divide that into two parts, I'm just storing anything that doesn't belong to train.a into a variable called rest. Okay, rest is vac of minus sam. So everything, so 60% went into train.a, the remaining 40% is sitting in rest. So now we want to divide rest into two parts. So again, we do a sample. This time we are doing rest $result. Result is the target attribute, but we are dividing rest into two parts. So we are doing rest $result. And this time I'm saying P is 0.5. Why 0.5? Why not 0.2? Well, because from what is in rest, we want 50% in one and 50% in the other. Okay, so that's what we did. So train.b is rest of SAMP and test is rest of minus SAMP. So we've divided the data into 60, 20, 20. If there's, I did 60, 20, 20 and not 50, 25, 25 because this is already a small data set. So I didn't want, train.a and test to have too few rows. Okay, so first we are going to use k equals 1. And the way in which you're going to do KNN function is to call the function called KNN. Okay, so what I'm doing is generating the predictions. The KNN function generates the prediction using the default cutoff probability of 0.5, or depending on if there are two classes, it's 0.5, essentially going by majority. Okay, and I'm putting the predictions that it's generating into a variable called, into a column called pred.1. Okay, pred because it's a prediction, .1 because I'm going to first create the predictions for k equals 1, so I'm just putting a 1 there. Now remember, this is just a column name that I'm making up, and I'm adding it as an additional column into train.b because we are going to generate predictions for train.b. Okay, so we are saying KNN, and the way the KNN function works is first you give the predictors in train.a, then you give the predictors in train.b. Okay, so you're generating predictions for this using whatever values are in this. Okay, and then you give the target attribute in train.a, and finally you give the value of k, which is 1 in this case. Okay, so these are the predictors in train.a, the predictors in train.b, and the target in train.a, and that's the value of k. Okay, so for k equal to 1, of course, there is no need for any cutoff probability or anything because you're going to get only one neighbor. So your probability is going to be 0 or 1. So if it is, of class 1, you say it's class 1. If it's of class 2, you say class 2. That's it. Okay, so really there is no need for generating any cutoff probability or anything. So for the case k equals 1, I'm just generating the predictions. In fact, that's what I'll do for the others as well. Okay, so here is our error matrix for the first k equals 1. Actual equals train.b $result, and predicted is train.b $pred1, which is where we kept the prediction. So this will generate our error matrix, and if I do tab.1, and this is the error matrix. Okay, it so happens that k equals 1 itself perfectly classifies everything. Okay, because this is a very small data set, k equals 1 perfectly classifies it, but the steps are exactly the same even if your data set was very large. Okay, so here I'm doing same thing for 3. Okay, so dot pred $pred dot 3, this is all the same except that here the k value will be 3, and then we generate the table pred dot 3. Okay, and then you find that the performance actually deteriorates with more neighbors. In this example, it's deteriorating. Of course, k equals 1 is hardly likely to be a good k value in a real data set. This is a small toy data set for illustration. Okay, so if you might do it for 5, 7, 9, etc. In this case, we have just done 1 and 3 for illustration, and I've shown you that with 3 the performance is actually worse, so we choose k equals 1. Okay, so now that we've got the value of k as 1, and of course train.a is there, we can now generate predictions for the test partition with the chosen k, namely k equals 1. So I'm doing test.$pred.1 KNN, and in this case, since we are generating the predictions on test, the second argument is not train.b, instead it's test. Okay, and by the way, one important thing to note that I seem to have skipped actually is when you give the predictor attributes, notice that I'm giving the predictor attributes as 4:5. Okay, the reason is that if you go back to our data set, which contains our scaled values, it looks like this. Okay, after converting, after generating the normalized values, it looks like this. So the first column is the unscaled income, the second column is the unscaled family size, the third column is the target. The fourth and fifth columns contain the standardized values of income and family size, right? So the fourth and fifth column make up our predictors, and that's the reason I used 4:5 for the predictors. Okay, notice that. And I use 3 for the target attribute because that is still in the third column. So now that we have this, we can generate the predictions for test, except that for test, instead of train.b, we do test, and we give the chosen k value, and we can generate the error matrix. Okay, in this case, in the data set is very small, performance is not that great. Notice that for buyers, the performance is only 50%. For non-buyers, the performance is about 60, 66 or 67%. Overall error rate is 3 by 7, which is quite high. Okay, but this is just illustrative, more to illustrate the steps than for anything else. I just want to highlight here the fact that for the training B partition, we try many values of k. We select a value of k. On the test partition, we only need to apply the selected value of k. In our present case, it was 1, but in general, it will be something likely to be something different on real life data, right? So there's no need to try many values on the test partition, right? Because after all, the test partition is only to evaluate the model that you've built. The correct value of k that you want to choose, that's part of the model building process. Once you have chosen that, you're only evaluating the model, right? So that is why we have to only try only one value of k for the test partition. So let's take a look at some other aspects. When you're looking at error matrices, there are many different ways in which you can display them. Till now, we've only been displaying raw numbers in the error matrix. Another option is to display the proportions, right? So our error matrix for test.1, for k equals 1 on the test partition, was stored in a variable called tab.test.1, right? In other words, we didn't just print out the error matrix, we stored it in a variable and then we printed out that variable, right? So we stored it in a variable for this reason. I can do prop.table tab.test.1 and then it gives me the proportions of the different cases, right? So this is totally, there were 7 cases. This is 2 by 7, this is 2 by 7, that's 2 by 7, this is 1 by 7. Okay, so you can get the proportions. Of course, all of them should add up to 1.0. So if you do prop.table, then you get the proportions for the entire table, right? But of course, notice that you don't want so much of precision, right? Two decimal places will be good enough for us. So we can just say round it off to 2 decimal places by doing round prop.table tab.test.1 comma 2. Round it off to 2 decimal places. So once you do that, you then get the values rounded off to 2 decimal places. Okay, that's one way of rounding off to 2 decimal places. Another way is, instead of doing round every time, one way would be to just tell the system by doing this is just a different way of doing the same thing. Instead of saying prop.table and then this, you can just combine the prop.table with the table generation in one shot. You can do that. It'll still give you the same results. Okay. One way is I'm setting here options digits equals 3. In other words, what I'm saying is, for going forward from this point on, only show numbers when you're displaying the numbers, show them to 2 decimal places or 3 decimal places in this example. Okay, so once you do that, I can then do prop.table tab.test and multiply by 100 to show percentages. Notice that I selected 3 decimal places, so it would have been 0.286 multiplied by 100 is 28.6. You can do that. Okay, now sometimes we are not interested in the overall proportions. Instead, we are interested in row-wise proportions or column-wise proportions. Okay, in which case you can do prop.table tab.test.1 comma 1. Right, so notice here that in prop.table we didn't give a second argument. Here we are giving a second argument, which is 1. Okay, if you do this, then you will get row-wise proportions. If you do 2, you will then get column-wise proportions. Okay, so if you want to see the performance on one class or another class, then you can use 1. Okay, so then you'll be able to see the row-wise proportions, which tells you how you performed on buyer and non-buyer. Okay, or if you want column-wise proportions, to say, okay, if the model says somebody is a buyer, then what is the probability that they are actually a buyer? If you want to answer that kind of a question, then you need column-wise proportions. You could use this. So let's look at how these two last options work. So if I did prop.table tab.test.1 comma 1, then notice the error matrix looks like this, right? So we are getting the row-wise proportions. So notice now that each row adds up to 1. Earlier, all the 4 numbers together added up to 1 if you don't give the second argument. If you give the second argument, if you say 1, then you will get row-wise proportions. If you say 2, then you will get column-wise proportions. Notice that in this case, the columns add up to, each column adds up to 1. In this case, each row adds up to 1.